So for this lecture, we're just going to review the strategies for integration that we have developed in the past few sections. And we will be following this sort of list of suggestions here. So I don't claim that this list of suggestions is exhaustive, or that it will, necessarily be able to give you a procedure for solving any integral. I mean, the fact is that for doing integrations, sometimes a little bit of creativity is required. But here is sort of the best that I can do to sort of summarize the techniques that we have looked at so far. So, first off, definitely the most simple thing that you can do anytime you're looking at a new integral is just see if it matches one of the basic formulas that we have looked at. So I have directed you towards this common derivatives and integrals cheat sheet before. That's on Paul's online math notes, so just do a Google search for it. So there's a big list of integration formulas on that. So certainly the first thing you could do would be to check if your integral appears on there. Next, if the integrand is a product of elementary functions, then try integration by parts, right? The method of integration by parts was developed so that we could deal with products of functions in some systematic way. Well, at least that's one of its utilities. If the integral is of one of these forms, so a product of sines and cosines or a product of tangents and secants, then we have a strategy specifically for that situation. If the integral contains trig functions at all, then it may be possible to use a trig identity to simplify it. And, it's not always obvious which trig identity you should use, so you should have your sheet of trig identities on hand to see if, maybe one of them would make it more simple. That just varies on a case-by-case basis. If the integral contains one of these expressions, so a big square root with a square underneath it, then you could try doing a trigonometric substitution. So trig substitutions were developed specifically to deal with integrands that have these forms inside of them. If the integrand is a ratio of polynomials, well, then you could try polynomial division, and then partial fraction decomposition to split that up into easier pieces. And then finally, if the integral doesn't match any of these forms, well, then you might have to make a substitution or do some sort of algebraic manipulation so that it does match one of these forms. And then you proceed from there. So let's just do a couple examples. Again, I don't claim that these examples are going to cover the entire ecosystem of integrals that you are likely to encounter, but at the very least, the book puts forth these examples as a sample. Okay, tangent cubed over cosine cubed. So I see that I have trig functions in here, and it is not immediately one of these forms. So I'm thinking maybe I can use a trig identity to simplify this. In particular, notice secant is the same as 1 over cosine, right? So since secant is the same as 1 over cosine, really, this 1 over cosine cubed that we have here, that's actually just a secant cubed. Oh, so this is actually already in this form right here. And we just had to do a slight manipulation to get it into that form. So our integral is, in fact, tan cubed of x, secant cubed of x. Okay, so now we can go about using the strategy for doing the product of tangents and secants. So feel free to look up your notes. This was the section called Trigonometric Integrals. Basically, when you're looking at something like this, if the power of the secant is even, then let u equal tangent and do a substitution. Or if the power of the tangent is odd, let u equal secant and do the substitution. So in this case, the power of the tangent is odd. So we introduce the substitution u equals secant x, and then do the requisite bookkeeping. So du is equal to, so the derivative of secant is secant tangent, and consequently dx is equal to 1 over secant tangent du. So now let's go ahead and plug that in. So our integral is tan cubed, secant cubed, but now since secant is u, we just write u cubed instead. Yeah, let me put a little space there. And then instead of dx, we write all of this. Only, in addition, because secant x is u, let's just replace that with a u there. Okay, so 3 u's up here, 1 u on the bottom. So one of those u's cancels, so we get just u squared. One of those tangents cancels, so we have tan square x left over. Oops, and this should be du. Now, we need to get rid of this x somehow. So we can do that by employing the trigonometric substitution. Or, that's not it. By doing one of the Pythagorean identities. So let's employ the Pythagorean identity. 1 plus tan square equals secant square. Right? Because that'll get rid of this tan square and have everything in terms of secants. So tan square is the same as secant square minus 1. And then, instead of secant, we can write u squared. Like so. Okay, and now we are in a position to just distribute that u square in, and then hit it with the power rule. Okay, and then finally just replace u with secant, and then we're done. And that is that. So, yeah. So this guy was actually one of these guys, but in disguise. We just had to do a very slight manipulation to get it into that form. Next. So e to the power square root x. Well, this is certainly a strange one. I mean, if we had just e to the x by itself, then of course we would already be done, because the antiderivative of e to the x is e to the x. But here we have this square root messing things up. So the only thing I can really think to do here is to just do a u substitution. Let u equal square root x and see what happens. And hopefully this ends up being in a more recognizable form. So then du is equal to 1 over 2 root x dx, and consequently dx is equal to 2 root x du. Okay, so let's plug that into the integral. So we have e to the u, and then instead of dx, I have 2 root x du. So we need to get rid of this x somehow, because we need this integral to be entirely in terms of u. So let's go back over here, u equals square root of x, and let's solve for x here. So solving for x, in the equation u equals root x, we get x equals u squared, right? Oh, actually, I'm sorry, we don't even need to do that. We don't even need to go that far, right? Because square root of x is already equal to u, so just plug that in. Yeah, so we don't even need to solve for it. Okay, the 2 is a constant, so we pulled that out front. So now what we have here is a product of elementary functions. So we have the algebraic function u times the exponential function e to the u. Well, when we have a product of elementary functions, that is the situation where integration by parts is going to be useful. Okay. So with integration by parts, we need to. So we're in a little bit of a trouble. We're in a little bit of trouble notation-wise, because in integration by parts, it is u and dv, u and v, but we already have the variable u being used here. So instead of u and v, let's call it w and v instead. So just recall the integration by parts formula is integral u dv, so let's call that w dv, is equal to wv minus integral v dw. Okay, so to choose w, we have our mnemonic I late. So I, inverse trig functions, nothing there. L, logarithms, nothing there. A, algebraic functions, yes. U is an algebraic function. So let's let w equal u, and consequently that means dv is going to have to be everything else. So dv is equal to e to the u du. Now we need to fill out the rest of the data. So we need dw, so that's going to be the derivative of u, which is 1 du. So yeah, no surprise there. And we need v. Well, v is going to be the antiderivative of e to the u du. So the antiderivative of e to the u is just e to the u again. Okay, so plugging this data into the formula, into the integration by parts formula, we get, and don't forget there's this 2 hanging out here, so we're going to have to multiply everything by 2 as well. So wv, so u e to the u, 2u e to the u, minus integral v du. So v is e to the u, or dw rather. dw is du. Okay. All right. So now we're essentially done, because this antiderivative writes itself. So we have 2u e to the u minus 2 e to the u. Now all we need to do, let me go ahead and factor that e to the u out, because that's bothering me. And I can factor the 2 out as well. So just u minus 1 left over. And now finally all we need to do is just replace u with what it originally was. So square root of x. Yep. So this thing which initially looked rather strange actually ended up being a perfectly ordinary example of integration by parts. It's just that it wasn't clear that that's what it was until we did a substitution. And that's sort of the theme for... That's been the theme for these past 2 problems, right? It's that it doesn't immediately look like something we've done before, but if you manipulate it just a little bit, then it is. Okay, so for this next one, we have x to the power 5 plus 1 over x cubed minus 3x squared minus 10x. So this one just screams partial fractions at you because it's a ratio of polynomials. So partial fractions is pretty much our only strategy for dealing with it. Well, provided the polynomials are of high enough degree. Right, if you had something like 1 over x squared plus a squared, that would just be an arctangent. So that's one of those formulas that's on your cheat sheet. But if it's anything more complicated than that, then it's going to be partial fractions. So try polynomial division followed by partial fractions. Now, in this case, is polynomial division actually warranted? Because you can only divide polynomials if the degree of the numerator is greater than or equal to the degree of the denominator. And in this case, that is indeed what happens. So here, the degree of the numerator is 5, which is greater than or equal to the degree of the denominator, which is 3. So we can do polynomial division. Alrighty, so let's initialize the algorithm. So n is equal to x to the 5th plus 1, and d is equal to x cubed minus 3x squared minus 10x. Okay, so let's go through the steps of the algorithm now. So first off, divide the leading term of n by the leading term of d. So x to the 5th over x cubed to get x squared. And then this gives us a term of the quotient. All right. Next, take the result of step 2 of step 1 and multiply it by d. So times all of this. And that gives us x to the 5th minus 3x to the 4th minus 10x cubed. Okay. Next step, take n minus the result of step 2. So take n minus all of this stuff. So let's see, x to the 5th minus x to the 5th, that cancels. And then nothing else interacts with each other. There aren't any other like terms. So let me write this in descending order. Oops. Got to be careful, because this minus and this minus cancel. So positive 3x to the 4th, positive 10x cubed, plus 1. Okay, and now that becomes our new n. Right, because in this step, we overwrite n with whatever we got here. Just double checking. Okay. Okay, so now we compare the degrees. So the degree of the numerator, or the degree of n, rather, is 4. And this is indeed still greater than or equal to the degree of d, which is 3. So go to step 1. So we are going to have to do another iteration. All right, so let me go through this a little bit more quickly. All right. So n is now 3x. Yeah, let me go through this more quickly, I say, as I proceed to stumble over the typing. Okay, so leading term of n divided by leading term of d. So 3x to the 4th over x cubed equals 3x. So that gets added on to our quotient. Next, take this times d. or 3x times d. So that gives us 3x to the fourth minus 9x cubed minus 30x squared. Okay, now take n minus this. And we get, so combine like terms, 3x to the fourth minus 3x to the fourth, that goes away. 10x cubed plus 9x cubed, so we get 19x cubed. 1, well, minus nothing. And I want to keep this in descending order. So all that's left is this 30x squared. So minus a minus becomes plus. Like so. And now this becomes our new n. Okay, now compare the degrees. So the degree of n is 3, and this is still greater than or equal to the degree of the denominator, or the degree of the divisor, which is d. So we need to do one more iteration. So we need to do one more iteration. So n divided by x cubed equals 19. So we get another term added on to the quotient, like so. Now take d and multiply it by the result. So times 19. So we get 19x cubed minus, what's 3 times 19? 57 minus 190x. Okay, so there's that. So now take n and subtract this from it. So 19x cubed minus 19x cubed, that goes away. 30x squared plus 57x squared gives us 87. So 87x squared plus 1, so that doesn't interact with anything. And then minus a minus, so that becomes plus 190x. So that becomes our new n at this step. Oh, why did it go to a new line? Whatever. Why did it go to a new line? That sucks. Anyway, okay, so now compare the degrees. So the degree of n is now 2, and that is no longer greater than or equal to the degree of 3, or the degree of d. So set the remainder to be the current value of n, and then we are done. So that is it for the division step. And then maybe after this we're going to have to do partial fractions as well, but, well, let's see. So we have q plus r over d. Yes, very, very ugly. Very ugly, this one. So let's see. These three terms are easy. We can just hit these with the power rule. So really, the only question has to do with this last term. So let's apply, if possible, the method of partial fractions to this dude to see if we can split it apart further. Okay, so how does the method of partial fractions start? Well, we always have to start by factoring the denominator. In this case, we can pull out an x. So we have x squared minus 3x minus 10 left over. And let's see, can we factor this guy further? I believe we can. So minus 5 plus 2, is that going to do it? So x squared plus 2 minus 5 is minus 3 minus 10. Yep, that'll do it. Okay, so we have a case 1 situation. We have a case 1 situation where the denominator factors into distinct linear terms. So the form of the decomposition is going to be as follows. Let me replace this with the factored form. So we are going to have one term of the decomposition for each of the factors. So a over x, b over x minus 5, and c over x plus 2. All right. Let's clear the fractions, because now we need to figure out what a, b, and c are. So we get so the denominator gets cleared out. Over here, the x cancels, but the x minus 5 and x plus 2 do not. Here, the x minus 5 cancels, but the x and the x plus 2 do not. And on the last one, the x plus 2 cancels, but the x and the x minus 5 do not. Okay. So for case 1, we have a relatively easy strategy for determining the constants a, b, and c. We don't need to equate coefficients. Basically, we just plug in convenient values of x. Yeah. So to get, well, let's see. Let's just start with over here on the left. So to get the factor x minus 5 to cancel out, so to get x minus 5 equal to 0, plug in x equals positive 5. Oh boy, now here we go. So if we plug in x equals 5, what the heck do we get? Let me just put this into my calculator here. So let's see. So this disappears, but we still have b times 5 times 5 plus 2. So let's see. So 5 squared times 87 plus 190 times 5 plus 1 is 3126. And on the right over here, we have 7 times 5, which is 35. So we get b is equal to 3126 over 35. And does that reduce by any miracle? That does not appear to reduce at all. All right, well, then, there we go. Okay, so that's b. To get x plus 2 to cancel out, because we're just gonna we're going to want to cancel out all of the linear factors which appeared. That's going to give us our constants, at least in case 1. So to get x plus 2 equals 0, plug in x equals negative 2. So let me spare you the details here, and spare myself the need to type them out more accurately. So if I plug negative 2 into the left-hand side, I get negative 31. On the right, x plus 2, these guys both disappear. So we have c times negative 2. Negative 2 minus 5 is negative 7. So negative 7 times negative 2 is positive 14. Okay, so c is equal to negative 31 over 14. That doesn't cancel, does it? I don't think it does. No, of course not. Okie dokie. So that's c. So finally, what's the only other term? So the only other factor that we have here is x. So to get x equal to 0, well, plug in x equals 0. So on the left we get 1. On the right we get, well, this guy and this guy disappear. So negative 5 times positive 2 is negative 10. So a is equal to negative 1/10. Alrighty. So that is our integral. That gives us this thing as split apart as we could possibly get it. So now this chunk here has been replaced with its partial fraction decomposition. Where a is equal to negative 1/10, b is equal to 31/26. These numbers are goofy. 31/26 over 35. And c is negative 31 over 14. And yeah, so now we can go ahead and integrate this. So the first terms are just the power rule. And then these last terms, these are all just going to be logarithms. Right? Because the antiderivative of 1 over x is log absolute value x. And same deal with these dudes. And that's all there is to it. So yeah, that one was quite involved. That one was quite involved. But yeah, ultimately just following the procedure as we've always done. Okay, next. So here we have another strange one that doesn't appear to fit into any of our standard categories. But I see this natural log x just like sort of hanging out underneath the square root, and that's very strange. That's very strange to me. So when I see like an obvious odd man out like that, just sort of hanging out where it doesn't appear to belong, that makes me think that the author probably has some sort of substitution in mind. So let's go ahead and let's do a substitution with u equals log x, and let's see what happens. So the derivative of log x is 1 over x. So this implies that dx is equal to x du. So now if we plug this into the integral, what do we get? Well, dx turns into x du. And on the bottom, we have x root u. Oh, well, how convenient. These x's cancel out. So we just get the integral of 1 over root u. So that's u to the minus 1/2. So now we can just hit this with the power rule. Easy. So yeah, this one was just trying to scare you. It's just trying to scare you by showing you something weird. But, you know, if you do that substitution, turns out there's not much to it. Why did I put this above everything else? Hang on. Okay. Let's see. So add 1 to get u to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2. And finally, just replace u with log x. And we are done. So that's all there is to that one. Okay, so here's another sort of strange one. So once again, it's not immediately obvious what we can even do with this. I mean, that big square root is certainly a little bit off-putting. And there's really no obvious substitution that we could make either. It's not like in the previous situation where we had this natural log sticking out like a sore thumb. Here's maybe what we can notice, though. I mean, we've got a big square root. What techniques do we have that can deal with big square roots? Well, trig substitution. Trig substitution deals with big square roots, except for trig substitution to work, we need there to be a square underneath the square root. Well, maybe we can do something to this. Maybe we can do some sort of algebraic manipulation to make it so that one of these x's becomes an x squared. Indeed, let's do that. So, in particular, if I multiply the top and the bottom of this dude by 1 plus x, and that is still underneath the square root, that is perfectly valid, right? Is that what I want to do? Yeah. Is that what I want to do? Let me do it the other way around. Sorry, I'm thinking ahead. Yeah, let's do it the other way around. So, okay, so this is a perfectly valid operation, right? Because this 1 minus x and this 1 minus x cancel. But now, notice on the bottom, we have a difference of 2 squares. So, on the top, we now have 1 minus x squared. And on the bottom, we have 1 minus x squared. So now this square root and this square cancel each other. So now we have this. So indeed, this is now a lot more amenable to trig substitution because we've got this dude here on the bottom, which, you know, that matches perfectly with one of the forms for trig substitution. And more than that, because I made that last minute change, we now have these two terms on the bottom. Whereas otherwise, the way I had been doing it, we would have the square root on the top and the 1 minus x on the bottom. So now, if we want, we can actually split this into two pieces. So 1 over root 1 minus x squared and x over root 1 minus x squared. And, well, let's actually go ahead and do that. Because now So now, so even though we started this with the idea of making trig substitution amenable, we actually don't even need to go that far, because that's an arc sine. Excuse me. That is an arc sine, by definition. And this, well, we can fix this by just doing a u substitution by, letting u equal 1 minus x squared, and then proceeding from there. So this just becomes arc sine x. And then, so let me just mention, let me just do the bookkeeping really quick.